We will now explore the behavior of the derivative of a function at its extrema. By extrema I mean a maximum or a minima. However, we do not necessarily require these points to be absolute extrema, but we just want them to be local extrema. So, for example, let us start with local maximum. We have already seen what we mean by global maxima or just maximum of a function. We say C is a maximum if f of c is greater than or equal to f of x for all x. Now a local maximum is not like if c is a local maximum, f of c is not greater than f of x for all x, but it's for all x that are sufficiently close to c. So this can be made precise as follows. We say f from I to R has a local maximum at C in I if there exists a delta such that f of c is greater than or equal to f of x for all x in c minus delta to c plus delta. So in this delta neighborhood of c, f of x is less than or equal to f of c. So this is the meaning of a local maximum. Similarly, we can define a local minimum as follows. We say f from I to R has a local minimum at C in I if there exists a delta such that f of c is less than or equal to f of x for all x in c minus delta to c plus delta. If it's either a local maximum or a local minimum, then we call it a local extrema. So local extremum is local max or local min. So this is the first concept that we have to understand. A quick picture might help us understand this concept better. So suppose we have the graph of a function as follows. Suppose something it looks like, say like this and like this and like this. Okay, something like this. Suppose this is the graph of the function. Now this point, if suppose this is the C, then this is a local maximum. This is not a global maximum because for these values it's bigger, right? For all these values, for all these x's, the value of the function is greater than f of c. But if you take a small neighborhood around this c, then in that neighborhood this is a maximum. So because of this, this is a local maximum, but it is not a global maximum. Similarly, this is a local minimum. We don't know whether it's a global minimum or not. If you want to make it not a global minimum, I will just continue this function a little bit and make the value of the function lesser at some other point. But this will continue to be a local minimum. Correct? Because you can take a neighborhood where it is indeed lesser value. The next theorem, called the interior extremum theorem, states that if a function on an interval attains a maximum at some interior point, that means not at the end points, then the derivative at that point, if it exists, has to be equal to 0. So let C be an interior point of the interval I. What is an interior point? It is not one of the endpoints. That's all what I mean by interior point. And we have that at which the function f from I to R has a local extremum. That means it either has a minimum or a maximum. If the derivative of f at c exists, then it is equal to 0. That means f dash of c is equal to 0. This is kind of intuitive because if suppose a function has a local maximum somewhere, then the picture looks like this, and at this point c, the tangent has to be parallel to the x-axis, which is the same as f dash of c is equal to 0. So that is the intuition behind this theorem. Let us now try to prove this. So we will prove the claim when c is a local maximum. The proof for the case when c is a local minimum is exactly similar. So how will we prove it? See, f dash of c can either be greater than 0, less than 0, or equal to 0. We will assume f dash of c is greater than 0, and that will lead us to a contradiction. Similarly, we will assume f dash of c is less than 0, and that will also lead to a contradiction. So because both these cases lead to a contradiction, we will have that f dash of c is equal to 0. That's the basic idea of the proof. Let us so now first assume the first possibility. That means case 1, which is f dash of c is greater than 0. If f dash of c is greater than 0, this implies that f of x minus f of c by x minus c is greater than 0 if x is close enough to c. That means there exists some delta such that f of x minus f of c by x minus c is greater than 0 if x belongs to the delta neighborhood of c. This is because f dash of c is nothing but the limit of this quantity. Okay, so now if you take f of x minus f of c, that is equal to f of x minus f of c by x minus c into x minus c. Correct? Now this will become greater than 0 if x is greater than c. And this is always greater than 0 in that neighborhood. If x is in c minus delta to c plus delta, if x belongs to c minus delta to c plus delta. So in this neighborhood, this quantity is greater than 0. So this product will be greater than 0. Product will be greater than 0 if x belongs to c comma c plus delta. So in that neighborhood, we will have f of x minus f of c is greater than 0, which is that f of x is greater than f of c. But that contradicts the fact that c is a local maximum. Hence, f dash of c cannot be greater than 0. So that is the for case 1. Case 2 is very similar, but let us quickly go over it nonetheless. So case 2 is f dash of c is less than 0. This implies that f of x minus f of c by x minus c is less than 0 if x belongs to c minus delta to c plus delta for some delta. Okay, so f of x minus f of c is equal to f of x minus f of c by x minus c into x minus c. Now this time what do? We do a little different. So this quantity is less than 0 if x is less than c. And this quantity is less than 0 whenever x belongs to c minus delta to c plus delta. So this product is greater than 0. This product is greater than 0 if x belongs to c minus delta to c, which contradicts the fact that, so this means that f of x minus f of c is greater than 0, that is f of x is greater than f of c, which contradicts the fact that c is a local maximum. So again we have a contradiction. So this case is also not possible. Hence case 3, that is f dash of c is equal to 0 is true. And hence we have the proof.